Our first speaker is Hanno Sahlmann, and as I mentioned in the morning, Hanno was one of the co-authors of this seminal paper on uniqueness of the kinematical framework of loop quantum gravity that was written with Jurek, Thomas, and Andre Okola. And today he's going to give a talk on a walk in Jurek's garden.
Thank you, Abai. Thank you very much. Can you all hear me, or do I need to speak louder? Seems okay. Just a very little historical addition, since my name was mentioned in terms of this lost result. While it was lost, Christian Fleischak completed a publication of a similar result, a related result, and he will, I guess, tell us about that and the other stuff later. Good. So thank you, everybody, for listening. Thanks for the organizers to put up this nice conference here, and thank you, Jurek, for bringing us all together in one way or another, as I would argue, in Jurek's garden. Let me start by showing some words, and these words are actually sort of words that appear in Jurek's publications, weighted with a frequency. What you see is that this is a very, very broad array, and this is testament to the fact that Jurek has really left his mark in many different areas, from classical gravity over mathematical physics to really quantum gravity and loop quantum gravity in particular. And one interesting way in which this shows is that we are at a conference where the title runs over 3 or 4 lines. I found this very nice, but it's really showing how much Jurek has done for many different communities. So what I want to do is I want to compare these ideas, these results, maybe also these paths, these open ends, with a beautiful garden, which I will call Jurek's garden. But certainly the nice thing about Jurek's garden is that it's not just Jurek's garden. He is there together with his friends, his colleagues, and some people work on some parts, some people work on other parts. It's not just Jurek's garden in a sense, it's all of our garden, but Jurek has given it a lot of beauty and a lot of nice things. He planted many flowers and many trees. So he planted small trees, and then by now they have become very big and beautiful trees, give pleasure to the eye, shade to postdocs and PhD students, and give us also new ideas about where to go next. And I could not possibly give justice to this garden because it's too big, so I will just look at a small corner of this garden and tell you a little bit about it, and then talk about 2 more recent works that I have done with some collaborators that extend the garden a little bit in that corner. So, as I said before, this is not just Jurek's garden. Many results here are Jurek's and somebody else's. And this is the case also for the result that I want to talk about today, or that I want to talk around today. And that is the so-called Ashtika-Lewandowski Hilbert space, which he invented and developed in collaboration with Abai, who's also here. And when I came to the field, this object fascinated me a lot, because at first it looks like it's something that's impossible to do. Yeah? So we have a Hilbert space of functions, in fact an L2 space, but it's a space not of functions, but of functionals, functions of functions. And these functionals are functionals on a highly nonlinear space, of the space of connections modulo gauge transformations. And when you know a little bit about mathematical physics, then you know that there are ways to do something like this over linear spaces, over vector spaces, also infinite dimensional ones, but this one looks like something completely different. And in fact, they were able to define the space, they were able to define a measure, and as I will explain, and even more Christian will later explain, there's a very special measure, a very special structure, and then this Hilbert space can be used for a lot of things. So the key to making this is, I think, to take this nonlinearity really seriously, not think of a connection as some form over some manifold or some bundle, but to think of the connection really as a map between path and a group. Thinking of it as giving a parallel transport, like when you have a path in a base manifold and you have a bundle over that base manifold, then parallel transport gives you a mapping between fibers of that bundle over this path. And if you want to summarize all the properties that these things have, these mappings have, then you can neatly say that these are groupoid morphisms from the groupoid of path under connection of path, concatenation of path, to the group viewed as a groupoid as well. And you can take this Hilbert space, and there's an orthonormal basis. This orthonormal basis carries labels. These labels are a graph, a network, and the networks are labeled. The networks are labeled themselves with quantum numbers, if you like, that are irreducible unitary representations of the group. The structure group in this context, I should say that the structure group is compact. That is important in this context throughout. And in the case this group is SU2, then you rediscover something that had been invented much earlier by Penrose, namely the so-called spin networks. And this, for me, is one of the magic of this construction, that starting from completely different ideas and completely different programs, you arrive at the same beautiful structure. Now, this Hilbert space is extremely important for loop quantum gravity because it carries a representation of the basic commutation relation of the theory. These commutation relations are written in terms of operators that describe the parallel transport and operators that describe the spatial geometry, in a sense, and I will refer to the parallel transports also as holonomies, and the variables that describe the spatial geometry are very analogous to electromagnetic electric fluxes, in fact, so I will sometimes call them fluxes. And these commutation relations can be rigorously represented on this Hilbert space, and while these canonical commutation relations were maybe in some form written down earlier, here you have now a solid mathematical framework to explore them, and this is what makes loop quantum gravity tick. Now, my plan is to tell you two things that I've done relatively recently to extend these ideas surrounding this Hilbert space, and they're not like big projects, very groundbreaking, but more like smaller things, but they're relatively fresh, and I hope they will show you that this thing is really a very rich structure that you can do a lot with. The first topic is about different representations of these commutation relations. And maybe before I go into details, so I should first say that this is done with a former master's student who is now a PhD student in Erlangen, Robert Seeger, and he's also here in the audience. I should say that what I've already hinted at before, that the Ashtikar-Lewandowski Hilbert space is very special for various reasons. And so it is the fundamental Hilbert space of loop quantum gravity. But in certain contexts, it can be interesting to generalize. And I will show one of these generalizations. So the first question is how can these operators, so first is if you take these commutation relations and now you want to find a different representation, then it might seem that now we are going completely away from this construction by Ashtikar and Lewandowski. We will get completely different Hilbert spaces. Everything will be different. And in fact, if you analyze the problem, then this is not the case. The most general representation under some suitable assumptions is a direct sum of L2 spaces. And now these L2 spaces are still on the space of generalized connections that Ashtikar and Lewandowski have defined, but they can carry different measures. And this is something that's enabled by their construction. There's not just the Ashtikar-Lewandowski measure, but there's a rich world of measures that one can put. And in this big direct sum, the parallel transporters will still be diagonal. They act as multiplication operators, essentially. The momenta will act as derivatives, and these are these black terms here. Those are functional derivatives that Ashtikar and Lewandowski defined rigorously in this Hilbert space. But then, in general, there can be more structure. They don't have to be diagonal. And they can mix these sectors, and some of the structure that is here, there are some constraints on this, but there's also a lot of freedom, apparently. Now, if you want to find a concrete realization of this more general picture, you have to think, what am I going to do? And the first and most simple idea you can come up is, well, I stick with one such Hilbert space, but I generalize the measure. And in fact, people have looked at this, and there are very, very interesting measures that have been defined by various people. One problem is that, as far as I understand, so far they don't support the flux variables as self-adjoint operators, so directly to apply them for loop quantum gravity is difficult, but they can, for example, be used as path integrals for Yang-Mills theory or something like this. Let me not talk about this more. This would be another talk about generalizing the measure. Let me say we stick to the Ashtikar-Lewandowski measure. Now, then, to realize this kind of structure, what we have to do is we have to go to more Hilbert spaces. And in fact, we can do that. We can build a tower of Ashtikar-Lewandowski Hilbert spaces. And as I said before, the holonomies will act diagonally. But now we can make the fluxes non-diagonal. And one of the simplest ways to do this is like so. Here we have on the diagonal the typical functional derivatives. And on the off-diagonal, we have simple things, numbers that are proportional to or operators that are proportional to the unit operator, just a number, and this number can be computed as a classical flux. One gives a classical densitized triad field, and one integrates it over a surface to obtain a flux, and those are these numbers. And so now you look at this and you say, okay, so what is this? What does it mean? Obviously, it is now not background independent anymore because we have some background classical field in here. So its interpretation in terms of loop quantum gravity is not so clear. But even mathematically, what is this structure? And the fact is that it is a representation where the fluxes, the spatial geometry, now has non-zero fluctuations even in the vacuum. In the Ashtika-Lewandowski vacuum, that's why it's such a fundamental vacuum, the geometry is, in a sense, has very low fluctuations, and it's basically degenerate. Yeah, there's no geometry. That's really the true ground state of quantum geometry. You have to make excitations over this very quantum ground state. But here we have in the vacuum already a non-vanishing covariance for the electric fields that fluctuate around some zero, some degenerate expectation value. And the states, the excitations that you have in this Hilbert space also interestingly are mixed for the holonomy. So also there you get some kind of different structures. And if you think about it a little bit, then you realize that due to these additional fluctuations, you can also get changes in the spectrum of the geometric operators. For example, the area operator, there will be new term coming from the fluctuations. Now, you can take this and generalize it. You can populate more of the off-diagonal elements. You can work with more general covariances. You can also have a condensate of geometry in the sense that the expectation value of this flux is non-zero. And one possible application that we have in mind is that in the early universe, we have a geometry that is not entirely classical, but that fluctuates. There are Gaussian fluctuations that are thought to lead to the structure that we see nowadays in the universe. And perhaps we can use these kind of states, this kind of Hilbert space, to describe this within loop quantum gravity, within at least effectively in the full theory. Now, there are many questions about this. One is that the fluctuations are very, there are few constraints on these, and that seems strange, or at least physically undesirable. We want to understand what kind of fluctuations are allowed and what not physically. So maybe this has to do with the next point. Maybe we have to think about the constraints and see if they allow us to, if they are allowed to be implemented in this. Maybe that reduces, again, the choices that are there substantially. And finally, something that I'm very curious about also in the states that in this kind of state, the geometry acquires, the spatial geometry acquires fluctuations, but in the ground state, the holonomy is still sharp, is still completely fluctuating. And the question is, can one maybe use this kind of vacuum that we have here as a stepping stone to get some kind of coherent vacuum where the fluctuations between the holonomies and the fluxes are a little bit more evenly distributed. I have forgotten to say this in the beginning. I should say this in the end. I said this is a representation of the commutation relations of loop quantum gravity. That was certainly very vague. And I would have to give a precise definition. And I should say that here we are kind of minimalist. So we're just assuming relations of the holonomies with each other and relations between holonomies and fluxes, but no relations between the fluxes themselves beyond what is required by Jacobi identities and so on. And so certainly if one asks more, then maybe these representations will not fulfill this. It's hard to say. So this has to do with the fact that we know that the flux variables have to non-commute in our framework. And this was always a little bit mysterious, but for example, you have written some very clarifying work about this. The question is how much of the relations that are there in the Ashtekar-Lewandowski Hilbert space do we want to impose? And here we just take the approach that we say what we really are, what is really important to us is the commutator between holonomies and fluxes, because that is defining what we do in loop quantum gravity. And beyond that, we only take what is required for consistency. But certainly that also implies that the fluxes are non-commutative. So with that, I want to leave the topic of new representations, and maybe fitting for Jurek's birthday conference, I want to look at the Ashtekar-Lewandowski Hilbert space in a slightly different way. And maybe this is interesting too, although, as I said, here we are not doing something new. We are just taking a new look at some classic thing. And this is also work done together with a master student, Benjamin Lotte. So I want to talk about holonomies, fluxes, and DHR charges. DHR stand for Doppler, Haag, Roberts. And these DHR charges is a notion of charge in quantum field theory that has been defined in the context of algebraic quantum field theory. And so I have to say a little bit about that, but like in the rest of the talk, I will be completely non-rigorous. So let me just tell you that algebraic quantum theory, well, it emphasizes the fact that in quantum theory, in general, we are dealing with algebras. That's the primary thing, algebras of commutation relations and so on. And then as a second step, we think about how can we represent them, what are the Hilbert spaces, and so on and so forth. And algebraic quantum field theory in particular organizes these algebras these algebras of observables by space-time regions in which these observables are localized. So formally, they are looking at a net that assigns to these suitable space-time regions an algebra of observables localized in that region. And these algebras then sit inside each other in a complicated way. And one thing that organizes this complicated way is locality. If you have algebras that are for regions with space-like separations, then it is required that the operators in these, the operators for these two regions, they sit in the algebra of a bigger region, and in that algebra, they are supposed to commute. And that expresses locality, certainly. And then there are more axioms, if you like, but I will not go into this. What you are doing at the end then is looking for representations of this kind of net of algebras. And in this context, one can now define the DHR charges. And to do that, one has to work relative to a vacuum representation, if you like, that is empty of charge. And the formal definition is that a DHR charge is a representation, or rather an equivalence class of representations, such that there is a space-time diamond, some certain compact set, such that if you look in the causal complement of this diamond, then your representation is just the one, then it is equivalent to the vacuum. So in other words, this DHR charge is something that is vacuum except for in some diamond. So one could think about this as, or could think about it as some localized charge, some charge localized in this region. And strictly speaking, I have to talk about equivalence classes, because certainly I can create these kind of excitations just by hitting the vacuum in this region with some local observable. But that is not interesting. That is sort of a charge that I can make and erase at will by just local operations. So one rather considers equivalence classes of these kind of representation modulo some unitary equivalence where the unitaries have to be out of these local observable algebras. So in other words, these representations, they differ in a local region from the vacuum in a way that cannot be undone easily. Now you have these algebraic quantum field theory axioms, and you apply them, and then you find that there's more structure than just these representations. One can show that to each such representation or equivalence class of representation, there's an algebra morphism that sort of creates this representation. So I can sort of rearrange the local operators, the local observables in a particular way, and then look at the vacuum representation, and that is equivalent to looking at the charged representation. So this kind of the charges are some kind of weird twisting around of the local observables. And this is nice because now these morphisms that are belonging to these charges, they give you more structure. Now suddenly you can, for example, add charges by composing morphisms. And there's even more structure so that at the end of the day, you find that these charged morphisms form a braided monoidal category. So there's some form of tensor product, and there is some sort of symmetry exchanging tensor factors, but in a potentially complicated way. And you can, for example, give the charges as statistics, and you can show under certain assumptions that there's only bosonic or fermionic charges, and so on. And interestingly, there are two big mathematical theorems about these charges. The one is that there is a mathematical equivalence, it turns out, between this big category of morphisms with all the extra structure and the category of unitary irreducible representations of a compact group. So what you find is, from this very simple-minded, in a sense, notion of charge, you get that there's a group that rules the charges, a gauge group. Yeah? And it's compact, and the charges correspond to the irreducible representations of this thing, the elementary charges. That's the one way. So you construct out of these charges this gauge group. And the other way around is also interesting. They prove you can get bigger algebras than your observable algebras, namely field algebras that carry charge, that can change the charge content of your representation. And then there's a big representation of this for these charge carrying fields. And if you restrict this to the observables, then it becomes reducible, and the sectors that you find are again these charged sectors. So you recover a lot of the structure that we usually associate with charges, but just from relatively simple assumptions. Now, what does this have to do with loop quantum gravity? Well, you can ask yourself, can we transplant some of this in this context? And well, at first you say, okay, they have space-time, whereas in our case, we just have a spatial slice. And when we think about space-time, then things become very fuzzy in terms of quantum geometry and causality and so on. But on this spatial slice, we have a notion of causal separation, space-like separation, because okay, so maybe I should first say, well, we can associate maybe these observable algebras with like some gauge invariant part of the holonomy flux algebra of loop quantum gravity localized in a region. And that is not great because these are not Dirac observables. These are just kinematical observables, so that is not really so physical, but let us do this anyway. And then what I was driving at already, if two sets on the spatial slice are disjoint, then in fact they are space-like separated. This is what we know. And so we have a notion of spatial separation. And in fact, you can also understand this commutation relations in the algebra very nicely, thinking about this fact that if things don't share a point, then they have to commute. Yeah? Now, obviously, the representation relative to which we work is the Ashtika-Lewandowski representation, and then we can run with it. And in fact, you can get something a little bit like embedding and something a little bit like reconstruction. And this embedding works at least for, and here something is missing. So in fact, this embedding just works for now for an abelian structure group. We have some ideas how to do it non-abelian, but let me talk abelian. Then we have morphisms that implement something like DHR sectors that are just conjugations of an observable with a spin network with open ends. And this is an algebra morphism, and it creates a representation that is different from the vacuum representation, if you like. And the charge sectors are labeled by the positions and charges of the open ends. And now, in fact, these are labels of a unitary irreducible representation of a gauge group, namely the gauge group that Ashtika and Lewandowski wrote down in their work that I cited in the beginning. There is a thing here that somehow, because we are looking at an abelian theory, there are no sectors with total charge non-zero, and that is because that kind of charge could not be localized because of Gauss' law. But I think we understand that. Now, reconstruction works always. We just take the gauge invariant observables as a sub-algebra of all, also non-gauge invariant observables, and we sort of factor the representation of the full holonomy flux algebra by restricting to the gauge invariant observables. And then again, we find this kind of sector structure where the sectors are labeled by the position and labels of charges of irreducible representations of the structure group. And again, these are irreducible, this label set, these are labeling the irreducible representations of the Ashtika-Lewandowski gauge group. Now, this is not something really new. You could have guessed this, but at least it is amusing to see that this part of this structure of DHR can also be found here. So what can this be good for? Well, it emphasizes something that people have said in the past, that somehow the open ends of spin networks, they are a little bit like particles. Yeah? And here you see in some sort of formal way, they really behave like charges. You can also ask whether is this all, or are there more general charged sectors? And this is something that I think is open right now. You can, this is also maybe interesting for the people that are doing algebraic quantum field theory, because when I heard about this from them, then they said, well, because there's a compact gauge group, this is all about global gauge principle. Yeah? But here, in fact, we have an example where this group is compact because of a certain interesting topology that is put on it, but it is actually a local gauge group coming from a local gauge principle. So with that, I want to close. I want to show the garden again. I want to say that I think if one wants to be high-flying, there's even like a book by Voltaire where he talks about the meaning of life and everything. And in the end, the protagonists of this book, they all figure out that the nicest thing is to go into the garden and work together and make the garden more beautiful. And so in that sense, I would like to thank Jurek very much for many days, many years in the garden, and let's all have more fun. Thank you very much.
Thank you very much, Hanno. Questions, comments? Yeah.
So in some of your slides, there was this scheme of quantization of algebra of local observables in space-time. Mm-hmm. So do you see we can in any way understand? And now the problem is that our kinematical algebra is not in space-time. It's actually only in some slice of space-time, and then we need Hamiltonian and dynamics to make it a space-time algebra. So do you see any way of approaching this problem different than just solving the quantum constraints and finding some effective Hamiltonian?
That's a very nice question indeed. This is something that maybe we should tackle. As I said here, there is causality here. Yeah, there is a causal structure, but it coincides with the sort of the structure that you just get from other sets overlapping or not. What is more interesting is to go into the future or into the past. And I don't know, maybe we can together figure something out, but I have no idea beyond that somehow in spin forms, they are talking about not only a spatial slice, but they are talking about like these vertices that represent structures like polyeders in space-time. Yet the mathematical structures are very similar, and so maybe we can learn from this in the canonical theory to see at least locally like a little bit of the space-time structure in our canonical theory.
Do you see any way to, within this DHR framework, find some field algebra which is related to a compactified version of the diffeomorphism group, maybe, not just of the SU2 gauge group?
Okay, that's a very good question, because indeed the analogy of I mean, in principle that should be possible. I would have to think about it.
Yeah, perhaps you might consider this things with boundaries and. Okay, in answer to what Jurek was asking, right? I mean, isn't there a famous paper by Lewandowski and Christina, which talks about
Indeed.
dynamics using a scalar field, right? I mean, which is so. Therefore, I mean, we can actually use relational time with a general scalar field. So, you're not happy with that, Jurek?
No, I just understood that maybe Hanno has some other idea of how we can approach this problem of how we can bring up some space-time causality. But I guess it was a different causality.
No, it's indeed space-time causality, but only on a spatial side. So it is causality, but it is very trivial in that case. Two sets are acausal with each other if their intersection is empty.
It's just disjoint.
That's what's on our slide. Thank you, Abai, for putting, saying the obvious.
Okay. Any other comments or questions? So, in terms of your new representation, the one that you mentioned in the beginning, which had to do with the expectation value of the flux to be 0, but the fluctuation is not 0. So, in that case, is there some simple relation between the expectation value of the area operator, for example, and this the background? Is it just the area of the background? Is something much more complicated, or what?
So, in fact, I think the spectrum of the area operator would get two contributions. One that would come from a non-zero expectation value of the triads, but then because it's like this square root of a square, also the fluctuations would go in. Right. And those contributions are a priori separate. So we have used here to make this covariance, we have used a background field, but maybe this is not the best way. I mean, it's not the best way to think of this in terms of a background field because these are fluctuations, so this is something different. But so I would say that if you have an expectation, non-zero expectation value, then definitely the area spectrum will be shifted by the classical, by this expectation value. And then if you have fluctuations, there might be additional terms coming from the fluctuations. Okay.
So the relation is not something simple because of these cross terms and under the square root.
Surprisingly, I mean, now we would have to look at the specific examples, but there is this thing which sometimes is referred to as Kozlowski-Sahlmann representation, which just has non-zero expectation values for the fluxes, but no fluctuations. And Madhavan Varadayan has actually really explained what is going on there. And there it turns out that the mixed terms go away. Right. When you go through the regularization procedure, and then what is left over is the background plus the quantum excitations from the spin networks. And it's a little weird that the spin networks can only add to the area and not subtract, but that's how it comes out.
Okay, so let us thank Hanno again.